Alrighty, I think it's about 6:01, so we'll go ahead and get started. So thank you all for coming to our critical design review. My name is Casey Ruckman. I'm a fourth year here at the university studying aerospace engineering, of course. And this is the critical design review of the Spaceport America Cup. Alrighty, so what is the purpose of the Spaceport America Cup team? As it's in the name, we compete in the Spaceport America Cup. That's hosted by ESRA, the Experimental Sounding and Rocketry Association, and that takes place June 21st through 25th in Truth or Consequences, New Mexico. So our team, we develop and present BSLI's most refined and technically advanced high-power rocket. And of course, we're trying to meet and engage with other members of the intercollegiate rocket community. Actually, real quick, I'll interject here. As you know, this is a Zoom meeting. All of the leads are here in the room. We're going to be taking off the mask when we're up here because we're sitting 6 feet away, and we hope it'll let you guys hear us better. So just by the way, and also if everyone could stay muted until question time, that'd also be greatly appreciated. Okay, back to the slides. Sorry. So what are the goals of our project team? So we want to have a nominal flight to 30,000 feet is the goal. We compete in the SRAD motor category, which is student researched and developed. Of course, we also want to stay safe and healthy during our meetings. So we're wearing masks normally when we're within 6 feet of other people and trying to be healthy so we can go to competition come June. We need to conform to ESRA's rules on designing our rocket so that it's successful. And also we pride ourselves in presenting a majority SRAD final design. So we only really need to do SRAD for the motor, but we want to have everything on our rocket SRAD, or at least as much as possible, because we really pride ourselves in creating everything by hand. And we want to supplement some of the academics with this hands-on experience. That's what we really provide to the OSU community. And of course, maintain a thriving rocketry community is a strong goal as well, because who doesn't like rockets? So what is our trajectory? Last year, the in-person competition was unfortunately canceled. Last year, though, we did have 2 successful flights. The first flight was to 7,500 feet, and the second flight was a launch to 12,600 feet. We did have an anomaly on landing, but we're looking to solve that this year, and we'll talk about that later. This year as well, we're staying focused on simplifying our integration process so we can continue to improve. By having checklists and being sure we can launch within the first day at the spaceport. We get bonus points if we do so. We want to continue advancing the current abilities of our sub-team, be more technical, continue to level up each year and get better. And we're targeting to have a test flight in late March of this year. Now I'll pass it over to my deputy project manager.
Hi, everyone. I'm Zach Parker. I'm the deputy project manager for the Spaceport America Cup team. Again, I want to thank you all for coming tonight. So I'm going to real quick go over an overview of our rocket. So we have 4 main subsystems within our rocket. We have our recovery system, our payload and avionics systems, which are both housed in the integrated systems bay. We have our telemetry, which is linked with the avionics system. And then we have our propulsion section and our propulsion system. And then we also have our structures team, which holds everything together, and our aerodynamics team to run simulations for us. So a few parameters for us. We have a wet weight of 64 pounds. A length of about 10 feet, a stability of 1.56, and our open rocket simulations project an apogee of 29,282 feet out of our 30,000 feet goal. We have a rail departure velocity of 92.6 feet, a maximum velocity of 1,898 feet per second, and an estimated flight time of 6 minutes and 36 seconds. So the way the CDR is going to work, each sub-team will present their purpose, an overview of their system, a breakdown of their system, their testing and validation, some risk identification and mitigation, as well as their upcoming spring schedule. Also, we have review item dispositions for feedback that have been, I believe, emailed out. They're in Slack, and they're also be linked in the Zoom chat here. And we will also be doing a 5-minute question session at the end of each subsystem. And after that, we ask that you hold all your questions until the end. You can either say your questions, unmute yourself and say your questions, or type in the chat, and we'll find the best to go. So we're going to start off now with structures.
All right. Hello, everyone. My name is Andy Ostovitz, and I am the structures lead for this year's 30K project. So the purpose of structures is pretty simple. We want to integrate the components that form the airframe as well as the internal housing for the other subsystems. We want to fabricate these components with the strength to survive a flight to 30,000 feet. This is our goal. So throughout the year, as we make these parts, we make sure that they will be strong enough to survive this flight. On top of that, we are also the most hands-on sub-team. So we have hands-on opportunities for all of our team members, and we let people kind of get those hands-on opportunities within an engineering team. So this is our system overview. Zach touched on this, but I wanted to go a little more in depth. So as he said, starting at the bottom, if you look in the bottom left, our internal subsystem housings. We have our booster tube section, which is our fins and motor tube. This houses the propulsion subteam. This has the motor casing as well as the motor. Then we have our transition. This has the antennas for the electronics that Avionics will be using. And then we have the body tube. The body tube holds the integrated systems bay, which holds the payload and avionics subteams. On top of that, we have the nose cone, which holds the recovery system, the parachute, shroud lines, and all that. The materials we use for our rocket, we have a carbon fiber epoxy composite, fiberglass epoxy composite, and aluminum. So to go more in depth with our nose cone is made of 6 layers of carbon fiber. It is 28 inches in length, and it is in a von Karman shape. It has a 6-inch shoulder that goes into the body tube. And this is made by laying up into a fabricated fiberglass mold. This is prefabricated because we're using the 2018-2019 mold. This mold has proved effective in the past, and we haven't changed our nose cone design. So we have the liberty to be able to use it again. We vacuum bag this, and then that's how we make this part. Similarly, our body tube has 6 layers of carbon fiber. It is 36 inches in length and 6 inches in diameter. Again, it has that 6-inch shoulder where it interfaces with the nose cone. We lay this up onto an aluminum mandrel and wrap it in shrink tape. Then we have our transition piece. This is 16 inches in length. It is the aerodynamic transition from the 6-inch diameter to the 4-inch diameter. It's made of fiberglass and is only 4 layers. As I said, the transition is used for the antennas, and this is because the fiberglass doesn't interfere with the waves quite as much as the carbon fiber does. It is only 4 layers because it's not an actual structural piece. It's only there for aerodynamic purposes, so it doesn't bear any load. So we have the ability to make it less layers. It weighs less, and it doesn't need to be as strong. We lay this up into a mold much like the nose cone, but this year we're making a new mold for this. Our transition piece underwent some changes, and you'll hear more about those changes and how we came to find those with aerodynamics next. We vacuum bag this much like the nose cone. Then we have our coupler. Our coupler is made of aluminum. It's 10 inches long, 6-inch diameter, 4-inch diameter. This is teamed up with the transition. This is the hard transition. This is what changes the loads from the 6-inch diameter to the 4-inch diameter. This is made of 2 aluminum tubes. They're welded together with the base plate. And we're getting this welded together externally through the OSU machining. So this is in progress currently. The recovery bulkhead, this is 6 inches in diameter. This goes between the nose cone and the body tube. And this is important because it's there for the purpose of pressurizing the nose cone. And this is important because if the nose cone isn't properly pressurized, the firing charges won't blast it off, and it could shoot black powder down into our integrated systems bay, ruining those electronics and ruining our flight, for lack of better terms. It's made of 2 carbon fiber bulkheads and an O-ring. The O-ring is between the two, and when we tighten those bulkheads, it expands. This will help us to get that pressure that we need. Has the 2 firing charges on top of it for blasting off the nose cone. And then it has the hardware, including the hook, which hooks onto the parachute. So our progress this year. So as you can see, we have the body tube, booster tube, and bulkheads all completed in green. Completed means finalized, means that we just need to finish them up by sanding and integrating them with the rest of the pieces once we finish those. The booster tube consists of an inner and outer motor tube as well as fins. So we have all of those parts ready, but those will only be used for our test launch, because for our exhibition launch in June, we'll be buying a booster tube. The body or the nose cone is yellow in progress, 1 completed, because we started last Wednesday with the nose cone. Truth be told, I have never made a nose cone, and no one on my sub team had made a nose cone previously. The only person on the team this year who has made a nose cone was Zach. So we started last Wednesday. We made our first nose cone for everyone. We got familiar with the process, and we made a pretty good nose cone. We do want to remake it because there are some things that we think we could do better. It'll be far more efficient this time. We'll be faster, and we know what we're doing. So next time we'll make a better nose cone, and the next one should be perfectly fine. On top of that, we have our coupler. As I said, this is external, so we're bringing this in. It's in progress right now. And then we have our transition piece. This is by far the thing that's going to take the longest. This is because it's also laid up like the nose cone, so it's just as difficult, but we have yet to make the mold. We have the plug for the mold being milled currently, and then what we're going to do is take that plug, make the mold from that plug. That should take a week, and then make the transition piece from that mold. That should take a week, give or take. And we'll have plenty of time, as you can see in the next slide, to do that. Not the next slide, later on, but sorry to foreshadow there. So testing and validation. So Structures has a high-level test plan. This basically means that we save our main testing until the test launch in late March. Throughout the year, we will be quality checking, but we can't really qualitatively say that our pieces are going to survive a flight until it has survived that flight. So this tests the entire integrated system and the strength of each of these components. From previous years, we know that these components will survive flights. A lot of them, save for the transition piece. Even the transition piece is still pretty similar, but most of them haven't been changed too much. So we know that these designs have survived before, but in order to say that these specific ones from this year will be able to, we have to have it touched down first. On top of that, this team specifically has been focusing on the mold release and mandrel press system. So we wanted to optimize that extraction. We've worked hard trying to figure out the best ways to where to bear down the way, a more efficient process for it. And I think we've got a pretty good way of going about it now. In the beginning, it would take us an hour and a half to pop off a tube. And then near the end, it was about 20 minutes. So I mean, they were different size tubes too. So you got to take that into account. But our team grew a lot in that aspect. And same thing with the mold release. And then the only other thing that goes with our testing and validation is the team education. And this is on there because throughout the year, I am testing in the sense that I'm not having members where I tell them what to do and then they go do it. I tell them what I need to have done, give them an idea, and then they kind of go off and get it done in a way that they see fit. I'm supervising, but this helps. So it's kind of a checks and balances where I'm not just telling them to make a part and they make it the way I want. They're going about it. So they're checking the way I would do it. And I'm checking the way they would do it. And this so we're cross-referencing the whole time. This is helping us to quality check throughout the year. And this is obviously going to be beneficial to future teams because we're just going to have a more educated sub-team. So our risk to our project success. So you can see we have A, B, and D all on the catastrophic loss of vehicle, but low likelihood. This is composite airframe structural failure, bulkhead internal component failure, or motor mount failure. These are all just some sort of structural failure or coupler failure. These are all some sort of structural failure that compromise the body of the rocket. These are low likelihood. We spend the entire year making sure these won't happen. I didn't want to put them at not likely because there's always an anomaly chance. So, but we do spend, this is our main thing that we're working against. This is catastrophic loss of vehicle. If something is to happen to one of these, then the rocket will not survive the link. C, bulkhead internal component failure. I have that significant critical impact. There's a chance that it's the same as all the others, low likelihood, but there's a chance that if one of the bulkheads inside breaks only slightly, we still survive the flight. It's still not going to be good for the flight, obviously, and we're still going to spend plenty of time working to push that off. And then finally, improper integration, not likely. That's our main thing. That one kind of covers all four, is all year, especially the last one I show you our schedule. The last month, we're kind of just making sure to integrate everything really well. It's going to fit together nice. We're going to integrate with the other sub teams, and we shouldn't be worried about that. That being said, our risk mitigation, we do those quality checks all throughout the year. That covers our composite airframe failure, bulkhead failure, and motor mount failures. As we quality check throughout the year, we're kind of working against any sort of failure in that sense. Our coupler failure, this is welded for strength, so it should be strong enough. It will be strong enough. The only thing that we have to make sure to do is check that it is parallel and concentric, so the centers line up so that our launch is, our rocket stands straight. As for improper integration, as I said, we spend all year making sure we're going to integrate properly. This is just if we happen to improperly integrate, then it would be an issue. But we do this all throughout the year, ensuring, and this ensures our efficiency on launch day, as Casey said or Zach said. We want to be able to do it in the first day, so we'll be quick with it and I'll be familiar. So this is our schedule. So as you can see, week 5 we have our CDR, which is currently happening. So looking forward, next week we're going to be working on our nose cone. That's just making our second one far more efficient this time. Then week 7, we're going to be working on a transition mold. Our plug will have been milled by then. We'll be able to make our mold. And then from there, we'll take that mold and make our actual transition. I imagine after the experience we'll have with the nose cone, we'll be able to make the transition the first time. But obviously we have those last 3 to 4 weeks of free space to be able to finalize those parts. If we have to remake another transition or happen to need to remake another nose cone or just need to stand all the pieces up and put them together properly. And then this is when we'll also integrate with the other sub teams to get ready for our test flight in week 12, the end of March, so that we'll be able to launch. And then after our test flight, we'll mainly spend time looking at what, if anything went wrong, or if there's anything we need to fix, need to make any additions or fix any of the parts at all. And then also we'll be getting that booster tube that we order in and integrating that. So now I can open the floor for any questions you guys have for the structures sub-team.
Yeah, I've got a quick one. I already wrote it.
Oh, go ahead.
You guys haven't talked about fins. Is that considered part of the structure? I take it that's later on, fin structure.
Yeah, so that'll go later on. You'll hear from that next from Aerodynamics.
Okay, that's fine.
John, you're on mute.
Okay, now I got it. Okay, so how do you do your structural testing for the new nose cone and for the cylindrical parts of the vehicle?
So structural testing that we do really is mainly our test launch. We make the pieces and then we integrate them together, and then we'll really see if they work properly at the test launch. We don't do anything where we put loads of weight on them to test, but since we've used these same pieces with these amount of wraps in the past, we have an idea that they will survive. And then, like I said, the test launch is our main source of actual tests.
Well, the test launch isn't going to be as rigorous as the 30K launch, is it?
No, it won't be, but this is what we're basing. If it survives our test launch, then we'll also be using a different booster tube as well. So really it's the nose cone and the body tube that need to undergo those things. So maybe we could look at in between, because we have those months in between the 30K launch and the test launch where we could look at doing different structural testing for those pieces. So maybe that's something that I'll look into, but I'll keep that in mind.
Okay, yeah, I think that'd be a good idea if you can do it. That's it.
Yeah, thank you, John.
I had a question about your coupler. You worry
Yeah.
about concentricity. What are you going to do to assure it's concentric? How concentric does it need to be? And I'm sure you didn't turn it out of a rod because of size and cost, but what's the thickness of the wall?
Hey, Craig. So I'll go ahead and take this one actually. So the way we do this is a little weird. Typically the PM's been handling the coupler, so I've been handling it this year. We're working on trying to pass it off. So I won't let Andy sink on this one. So the coupler is, the upper tube is an eighth inch thick wall, so 0.125. So it is pretty thin. So that is a large concern, is deformations and also ensuring things are aligned. So we've been working really closely with Kevin over here in the OSU machine shop to try to make sure we get that concentric. So last year we did have an issue with the angular alignment was off. So we're trying to make sure we have a good process, and we're actually going to use some, not forms, but like some extra structure when we go to weld it together to ensure it stays aligned as much as possible. And then from there, we'll be able to measure and see, as long as we're within specified thou tolerance and angular alignment, we'll be good to go.
Okay, thanks.
Yeah, of course. Back to you, Andy.
Yeah, what Casey said. Thank you for stepping in on that one. Any more questions for me? Structures in general. Any in the chat?
You say that's aluminum. What aluminum is it?
6061.
6061.
The temper.
Yeah.
Um,
Can you restate the question?
What is the temper of the aluminum you're using?
Sorry, 6061 T6. My apologies.
T6. Okay.
Yep.
And it's going to be welded right at the 90 degree between the two sections.
Yeah. So if you go back to the coupler, Andy. Sorry.
my bad.
All right. So I'll use the laser pointer on the screen here. So yeah, it's going to be welded under here. So that's going to be a flat plate. It'll be welded in there. And then this outer joint's a little harder to do, but we can chamfer. So there'll be a plate that goes inside the 6-inch tube. We can put a chamfer on there and then weld it. And we might turn it down just to get some of the bead off if we need to, but we don't actually need that for any aerodynamic or reasons for fitment. So we'll weld those two positions.
Aluminum's tricky to weld. You got to know somebody who can weld.
Yep. There is a person over in the physics department that helped us out last year that we're planning to talk to again. If not, BSLI's recently made a connection with the Pipe Fitters Union, which is actually just over on Kenny Road, right by CDME, or Kinnear Road,
Yeah.
sorry.
Yeah. I know.
And we could go talk to them as well.
All right. Thanks.
Yep.
Cool. All right, so if that wraps up questions, then I'm going to pass it on to Aerodynamics.
All right. Hello, everyone. My name is Stephen Morosky. I am a third-year aerospace major here at Ohio State, and I am the aerodynamics sub-team lead. All right. So what is the aerodynamics main purpose? Our main purpose as a sub-team is to define the rocket's performance through all phases of flight and determine the drag and stability of it. And also, we want to make sure that we give our team members some good experience, hands-on experience on CFD and how it's kind of used in industry and how we can couple that with our aerodynamic knowledge we learn in class. All right, so the overview of what our sub-team does, again, we get accurate drag estimates for all regimes of flight, not just max Q. We want to recommend geometry changes, as we will show today based on our simulation results. We want to assess the stability throughout all phases of flight and make sure that we're statically stable through all phases. We also want to make sure we gain confidence in our simulations. This is something we're constantly striving to do, just trying to make sure that what we put into the computer, what we get out of the computer is reliable and that we can really recommend things based off of that. And then once again, we just want to make sure that our team members gain knowledge on how to use CFD and then how to properly analyze results. All right, our general design process for how we design different parts or how we go about our simulation process is that first, if we're making design changes, we want to try to look up some current literature and see if there's anything out there that we can maybe model our designs after. And then after that, we're going to move into our preliminary 2D axisymmetric runs at max Q. 2D axisymmetric is less computationally intense than 3D. So we just start with that. And then after we get max Q down, we move on to testing the other regimes of flight. And then once we've decided on a shape from 2D, we're going to import it into 3D and once again, try to run everything through all the different phases of flight. All right, so right now we're going to look at the transition piece design. So this is a slide from the PDR, and it shows how we had previously tested conical versus convex versus concave. And really, we didn't see any major drag improvements just by changing the shape of our transition piece. So what we decided to do was increase the length by 2 times, and we saw a significant drag savings. So we decided that that was going to be our variable we were going to investigate. All right, so for how we decided these lengths, we have our current length of our transition piece, 1.5 times 2 and 2.5 times our current length. One thing we also did was we changed the shape from our original shape here in the top right, which kind of has these squared off corners, to this Bezier spline, which kind of has a more smooth curve. It might not come out quite perfect in manufacturing, but it's there in the simulations just as an ideal case. All right, so the next thing we had to do was define our simulation parameters. So what we did was we ran an open rocket simulation, and we started at Mach 0.3, or we took our design points starting at Mach 0.3 right after liftoff to Mach 0.3 right before apogee. So as you can see here, we tested 17 different design points throughout our flight. And once again, these are from our open rocket simulation. All right, as for how we set up our simulations in Fluent, we use the realizable K-epsilon turbulence model with scalable wall functions, which is targeting a Y plus of between 30 and 300. We used a pressure-based solver, and then we used a quadrilateral dominant mesh, but we had to use 2 different meshes for these simulations because for supersonic, we were going to use adaptive mesh refinement, which means that the solver automatically refines the mesh around a parameter we chose. So we chose pressure, so it refines around the shocks. And then in subsonic, there's not really any variable we wanted to refine around. So we just put a tight box in around the rocket to make sure we got good resolution around there. All right, one thing I want to mention quickly before we get to the results is that, as I mentioned on the last slide, we commonly refer to this parameter of Y plus. Really, basically, Y plus is this parameter used by our solver to calculate turbulence. And like I said before, it should be between the value of 30 and 300. But when we used adaptive mesh refinement, along our transition piece, it refined the cells and it made our Y plus drop into an unfavorable region where we don't want it. And as you can see, that's on the top here. And on the bottom is without adaptive mesh refinement. So, but I think despite this, with some of the qualitative and quantitative results I'm going to show you, we still have enough confidence to recommend a geometry change. All right, so this is our simulation result. So these are the max Q contours for our current length, 1.5 times 2 and 2.5 times our current length. So you can see that the shocks came out nice and clear. But with this picture, it's kind of hard to see much detail with it. So we went ahead and I'm going to show you these pressure contours instead. So one thing I wanted to point out with these pressure contours that was pretty interesting was as you increase the transition piece length or kind of decrease the angle that it's at, you can see that the pressure gradient from free stream to after the expansion wave, it seems to decrease, which is also something we found when looking up literature is that in theory, as you decrease this angle, that pressure difference should be lower. All right, so then going back to our design points, like I said, we had 17 different design points for 5 different transition piece shapes. So this is all our total drag results plotted out versus time. So you can see that as we increase our transition piece shape, it decreases drag pretty significantly. And over here on the coefficient of drag versus Mach number, you can see that the transition piece really has its greatest effect in the supersonic regime. One anomaly I'd also like to point out is right here at these 2 time slots, right, how they differ kind of oddly from the open rocket prediction. That was right around Mach 0.9 or Mach 1, which is really hard to simulate and get right. So that might be why some of those values are just a little off from open rocket, or it could be that open rocket doesn't predict it, right? We're not entirely sure the reasoning. All right, so then the question is, how are we going to determine which shape is the best? Because obviously if we're increasing our transition piece length, we're adding weight. So, okay, so we need to figure out how much drag are we saving versus how much weight are we adding? So the first thing we did was we integrated all those curves you saw on the last slide, divided them by the total time from liftoff to apogee. And so we get what we call the average drag of each transition piece. So you can see, it gets this nice curve here that as we increase the transition piece length, obviously we do get this decrease in average drag. And here at the bottom, it's plotted in the angle of the transition piece versus average drag. The next thing we had to do was to account for the weight. So we weighed our transition piece and we found it was around 2 newtons. So we set that as our base weight and said if you double our length, we're going to add 2 newtons. So we're going to double if you double the length, we're going to double the weight. So then we added this average drag curve and then this weight added curve, and we get this drag plus weight versus transition piece length. As you can see that even as we increase the length, we're going to decrease drag and not add so much weight that we're losing the drag we're saving. But that wasn't quite sufficient for us. We want to make sure physically, back down to physics equations, back to Newton's second law, that we are in fact going to go higher. So what we did was we did a Simulink analysis. So we said force equals mass times acceleration, which for us is going to be equal to the thrust minus the drag minus the weight. And we rearranged everything for acceleration. One note real quick is that this is an extremely idealized model. We're assuming no motor exhaust in all these simulations, no angle of attack, and no fins. So in Simulink, we took this acceleration at each step and we integrated it to velocity and then height. And so as you can see, as we increase our transition piece length, even with adding weight, we will indeed go higher. So in conclusion for the transition piece design, we decided on 15 inches or about 1.5 times our original length. This was chosen because it gives us a pretty significant raw drag savings, but it's still short enough that structures knows how to is going to be able to manufacture it easily. And also we never manufactured something longer than what we currently have. So we want to make sure we can do it. We also didn't want to make it so long that we're going to start disturbing the flow around the fins. But also one really cool thing that was pointed out with the Simulink analysis is that it's kind of a proof of concept that maybe we can work towards making our own altitude predictor from Open Rocket. But that would require 3D sims. And well, we managed to get some 3D sims in before the CDR. So these are our preliminary 3D quarter body results, which means we simulate a quarter body of the rocket. And then we assume that this plane on the right and this bottom plane are symmetrical. So the solver just sees that flow as being symmetric across that plane. We did use adaptive mesh refinement, and then we used the same max Q conditions at Mach 1.7 as for the transition piece simulation. So here are those results. You can see we're predicting a total drag on the rocket of 820 newtons. You can see that the nose cone and the motor tube are both the two biggest contributors, which makes sense as the pressure drag is what's going to dominate the drag on this rocket. And you can see that compared to open rocket simulations, a drag of 820 newtons is pretty close. But something I should mention is that open rocket does not actually predict the change in drag with our transition piece length change. So these 3D simulations is what we're going to really try to rely on and build an altitude predictor for trying to get us close to 30K as possible, which is something we're judged on at the competition. All right, risk to project success. The first two, overestimation and underestimation of drag. I put them both as likely just because I think CFD is a really difficult, complex program. And I think with the level we're at and the turbulence fidelity model we're at, we're not going to get the drag perfect. So I said it's probably likely that we're not going to get it right on, but it's not something that's going to make the rocket break this year, or because we designed this structurally so that it could withstand high loads. But it would be a significant impact to our judging because we might not get exactly at 30,000 feet. The next one, static instability. I'd say this is extremely unlikely as we use open rocket to determine this, and it generally is accepted as a pretty good predictor of stability estimates. And the last one is fin flutter, which is low likelihood because we buy the fins commercially and they should be rated up to a certain Mach number. And we also use different a fin flutter estimate software. All right, to mitigate these over and under prediction of drag, we're going to work on trying to get some hand calculations. We haven't done this yet, but I'm going to really try to emphasize as we move closer to the competition that we have some to verify our model. We're also going to look at doing mesh independence studies, so changing the mesh size and see how that changes our results. I also want to test different turbulence models and see what that gives us in terms of different results. And then obviously, if we have this altitude predictor, try to get a way of validating our model with the test flight we do in March. Next, for static stability, again, some basic hand calculations can probably be done to verify that we will be stable, as well as comparing it with open rocket. And then fin flutter, we use a commercial we use a software that's well accepted in the community, and that is based on a lot of textbooks that know a lot about flutter estimates. But we can always look into other fin flutter estimate models. All right, so for the schedule, February through March, we're going to keep running 3D sims to try to get sims of the 30K configuration and the test flight configuration, just because they use different fins. We're going to begin trying to develop this altitude predictor, whether it's a plugin into OpenRocket where we can just change the drag values, or if we have to create our own through a Simulink model integration. We're also going to research trying to run sims with motor exhaust, and then I'll try to do more hand calculations. And then April to May, really finish this altitude predictor, get it ready for competition, make sure that we can hit as close to 30K as possible. And then we're also going to validate our simulations with the test flight, more hand calculations, and then just general prep for competition. All right, any questions?
Steve, John Dilley. Hey,
Yes.
That can be kind of tricky. I did an analysis about 3 years ago on base drag and some experimental data from back in the 50s, I think.
Right.
Do you have that stuff?
Yes, I'd be interested in meeting with you maybe at one of our meetings, because I did read through it. I was just a little confused about what exactly the conclusion of the analysis was. So maybe we could meet and talk about how exactly we could integrate that with our rocket.
Sure.
But yeah, that'd be interesting.
That'd be fine.
Okay, sounds good.
I got a quick question. Who'd you buy your fins from?
Binder design.
Binder design.
Oh, okay. I might look into that. Okay.
Good stuff.
I had a quick question. Why do you think drag went down as you increased the length?
So as in our mock charts, I think one reason it decreased is because as we increase this length, the wave drag probably decreased. So the pressure difference between free stream and right behind the shock is not quite as extreme. There's not quite as low of a pressure right behind that expansion wave. So I'm guessing the difference between that free stream pressure and the pressure behind the expansion wave being less probably is what led to our decrease in drag.
I have a quick question. Out of
Yep.
curiosity, do you have plans to validate your models with physical testing, either through like a small scale wind tunnel or maybe like pressure taps on a test flight? Just curious.
Right now, we don't have any plans for like pressure taps on the test flight or wind tunnel validation. That's something that I think would be good in the future to do. I'm not sure we'll have time to do it this year. But the one way we're really going to try to validate it is with this altitude predictor and just trying to see, are we at least within the ballpark with some of these simulations? Because yes, validating our results is one of those things I've always personally struggled with looking at these simulations. I'm like, well, how can I really trust this? And I'm always like, okay, if someone asks me, how are we going to validate our model? How valid is our model? I need to have a good answer to it. But yeah, we're going to validate our altitude predictor with the test flight. We're going to simulate the test flight rocket and then predict its altitude with our altitude predictor and check it at what we actually get.
So the major input into the altitude predictor is just the drag?
Yes. So we include thrust and weight.
Yeah.
But the main thing that we're changing based on OpenRocket, which is the program the team's used for many years now, is that we're going to actually input our own drag data, which we've never done before.
Is that a variable input then?
Well, in OpenRocket, there's currently no way to change the coefficient of drag that it uses at each Mach number, but there are some plugins I found online that might let us do that. And also, if we develop our own through Simulink, we can just take whatever drag values we get from our simulations at certain Mach numbers and then put that into this predictor and say at this Mach, between these Mach ranges, use this drag value.
Okay.
Does that answer your question?
What you really want is a plot of drag coefficient versus Mach number.
That's right.
Yes, right. So we could do something
But
like
you
we
can
did.
put that into OpenRocket, can't you?
Well, right. By default, there's no way to input this coefficient of drag versus Mach number. Like I said, I looked up about a week ago. I found a plugin that might work, but we just haven't had time to test it yet.
Because you could really overshoot your altitude or undershoot it.
Right. I mean, that's one thing that's really difficult to try to validate, which is why we're going to try to use our test flight rocket model to try to figure out like how is our altitude predictor actually predicting our altitude, I guess.
So I'm certainly no rocket expert. Your inputs are drag,
Yeah.
thrust,
Yeah.
and what else?
Weight.
Of course, weight. Weight,
Right.
Thrust,
Yes.
pretty well.
Yes, we with our propulsion team, they will do a static fire of the motor we'll be using at competition, and then we'll take that static fire they do and just plug that straight in to the simulation.
So it's all about drag.
Yes, right. So at the end of the day, the only variable thing that could change the altitude really comes down to drag and angle of attack if we add that in the future.
Yeah, okay, thanks.
Yes, no problem. Any other questions?
Have you tried to look at prior test launches in order to validate this analysis here?
We have not looked at prior test launches yet. I think one of the main things is that we don't really have good, there's not really great documentation of past test flights, and it's very hard to find. And we still need some time to develop the model. So I think our test flight will kind of land right around when we're ready to test the model. All right, any other questions? All right, next up will be avionics.
All right. Hello, everyone. My name is Joe Heiser, and I'm the avionics subteam lead. So our project purpose is to design and build a high reliability avionics system to control critical functions of the rocket and to collect telemetry to safely recover the rocket and analyze the flight. Another one of our goals is to educate team members in electronics design, software development, and system integration to be able to produce a robust avionics subsystem. So some of the requirements of the avionics team is to obviously deploy the drogue and main parachutes at the correct altitudes, record and transmit flight data, safely arm and disarm the rocket, and track the rocket for recovery. So starting with the system overview of kind of the bay structure itself, on the left, you see a CAD model of our avionics bay. So it's a 2U Cubesat form factor. We have a modular board design. So there's a backplane on the bottom, and then the boards slot in with wedge locks, and they're locked in place to the aluminum structure of the bay. So the rails and those 3 bulkheads are all made out of aluminum. On the right side, you see a prototype. So those rails, the aluminum rails, are the final versions, and the backplane you see is also the final version. But those red plastic pieces are going to be milled out of aluminum. They actually are milled already. They just need some holes tapped, and then they are complete. So here's a schematic overview of the system. So you can see here anything that's connected to the CAN bus down here where the laser pointer is going is what's actually in the avionics bay on the rocket. So on the previous slide, what you saw, we have the backplane, which is kind of represented as the CAN bus here. We have these green boxes are all of our custom boards. So we have the custom flight computer, the custom telemetry transmitter, the 2 arming boards for the commercial flight computers, and we have a camera arming circuit. And all the arming circuits for the camera and the commercial flight computers are the same circuit designs. That allows us to have an easier development cycle. And then up here on the left, you have the telemetry receiver and a computer laptop. And you have these like little antennas, so you can see the telemetry receiver connects wirelessly to the telemetry transmitter on the rocket. So I'm going to talk about some of our boards in the rocket, starting with the power board. So the power board obviously supplies power to all of the other modules on the rocket, and also regulates our battery voltage down to voltages that the other boards can use. So we have about 38 watt-hour lithium ion, it's a 4-cell lithium ion battery. That gives us 10-hour battery life, greater than 10-hour battery life at full power modes. That's with our telemetry transmitter transmitting at high power mode. That's like the most power we'll draw, and that's over 10 hours of battery life. And then in low power mode, we have over 50 hours of battery life. So that gives us plenty of time for integrating. If integration takes a long time and if we're out on the pad for a long time, we have no risk of running out of battery. The power board also provides battery charging and cell balancing, so there's no need to de-integrate our avionics bay. So we don't need to take out a battery to charge separately. We just plug in a wall adapter essentially to the avionics bay, and it charges the battery and does all the cell balancing. Like I mentioned, the board regulates the battery voltage down to 5 and 3.3 volts using a switching regulator. So that's over 90% efficient, again, to help increase our battery life. And finally, it provides telemetry over the CAN bus. And this is a thing that all of the modules do. So we were able to send information like battery voltage and current, battery temperature, the voltage and current of our 5.5 or 5 and 3.3 volt rails, and things like that. And that's all sent to the ground so we can monitor the health of the rocket and the battery. So next, we're going to talk about our commercial flight computers. So these are 2 commercial flight computers we've used in the past. They deploy the drogue parachute at apogee and the main parachute at 1,000 feet. And these are reliable. And like I said, we've used them in the past and it's always worked well. And they act completely redundantly from each other. So we have full redundancy all the way through. So the arming boards are what controls power to the commercial flight computers that I just mentioned. So the arming boards each have their own commercial flight computer and their own battery, and a redundant connection to redundant recovery charges. So it's redundant all the way through. We're using a latching relay to control power to the commercial flight computers. So this allows us, if there's a power loss on the control side, if there's a power loss on the control side of the relay, the state is saved. So if we arm the flight computer and we lose power for some reason, like the main battery dies or something, the state will be saved and it'll stay armed. Or if we have the flight computer disarmed, it'll stay disarmed if anything else happens on the rocket. And these relays are rated to 50 Gs for shock and vibration, so they'll be able to withstand the environment and rocket flight. And again, like all the other boards, this provides telemetry data, so we'll be able to read the flight computer battery voltage and current to monitor the status of the commercial flight computers. So here's our custom flight computer. It's based on a Raspberry Pi Zero for easy software development. It's used to arm and disarm the commercial flight computers via our telemetry link. It also collects GPS data, pressure, acceleration, orientation, and it kind of corroborates all the telemetry from the other modules, and it's stored locally on the Raspberry Pi and also sent over our high-speed telemetry link to our ground station. And it plays a passive role for research and development and for our high-speed telemetry. So it has no authority to control recovery charges. That's all left up to the commercial flight computers. So here's our command and telemetry modem. We're using two RFD 900Xs. They're high speed, long range, up to 40 kilometers line of sight, two-way radio modem. So we use these to transmit telemetry to the ground from the rocket at a much higher data rate than we can do with the commercial solutions. And they also, we can send arming codes, we can send high, low power control commands, we can start recording, stop recording of the camera, all remotely from range using these radio modems. And we use Ball Aerospace Cosmos to receive telemetry and send commands. That's kind of used in a lot of satellites in the industry, and it's kind of typical for command and control of aerospace systems like this. So our commercial telemetry, this is a redundant system that's going to be housed completely in the transition piece, which is, we also have all our antennas in the transmission piece for to be able to pass our radio signals through. But the tele-GPS is housed completely in the transition piece, and it's used to redundantly track the rocket throughout flight. It's on a different frequency than our custom telemetry solution, so there's no interference there. So testing and validation. First, we have battery life tests. So although the battery is rated for a really long runtime, we're still going to test that to make sure that it will last what we expect it to last. Environmental testing. So we're going to bake the Avionics bay in the paint cure oven that we use for like paint and epoxy curing to simulate temperatures that will be experienced inside the body tube when we're like sitting out on the pad at Spaceport America. Range testing, we're going to verify that telemetry solution meets the required range. It's rated for 40 kilometers line of sight, but with our specific antenna solution and everything, we're going to test that. And we can also verify or receive signal strength on the rocket and on the ground station. So at all times, we'll be able to see kind of what the strength of the connection is between the rocket and the ground station. And finally, software testing, we're going to write test cases to test difficult conditions to verify software integrity. So now some risks to project success. We have, so a single flight computer failure would be a significant non-critical impact. If one flight computer fails, we still have the completely other redundant system with redundant recovery charges. So that would be a significant but non-critical impact. Dual flight computer failure would be a catastrophic loss of vehicle. So that's a big failure. Obviously, if both computers fail, we can't fire recovery charges. So C, a main battery failure / loss of charge. Again, a significant non-critical. If the main battery fails, the flight computers would have already been armed. And if they weren't armed, then we won't launch. And like I said, if the main battery fails, it doesn't affect the arming state of the main flight computer or the commercial flight computers at all. D, a wiring harness failure would be a significant critical impact. So that's assuming kind of a non-complete failure of the wiring harness. So that's the wiring harness from the flight computers to the recovery charges. There's 4 recovery charges, 8 wires total. So that's kind of assuming a non-complete failure. So like not all 8 wires breaking. So that's why it's a significant critical impact, but we should still have some connection to recovery charges that would allow recovery to happen successfully. E, base structure failure. So that's probably a catastrophic loss of vehicle if somehow the bay was compromised, but it's built completely out of aluminum and is really structurally sound. So that's not likely. F is loss of GPS reception. So that's low likelihood, slightly higher likelihood than the other things because we have a lot of antennas kind of packed into our transition piece, and sometimes we have reception issues with that. But for at least our custom telemetry and flight computer solution, we're using a high gain GPS antenna. So we should have pretty good GPS reception throughout flight. G is telemetry connection failure. So that's kind of the same thing I just said about the GPS reception. We have a lot of antennas packed in there. So it's slightly higher likelihood than the other things that could fail. But again, a non-critical impact because if we lose telemetry connection, we have a redundant telemetry and it's not a huge problem. Finally, H, CAN bus failure. So again, that's a significant non-critical impact. All of the modules communicate over CAN bus for telemetry. We also have redundant lines on the backplane to be able to arm the commercial flight computers directly from our custom flight computer and telemetry solution. So we can switch the relays directly from the Raspberry Pi essentially. So if the CAN bus is down for some reason, we still have that redundant ability to arm and disarm the rocket safely. So risk mitigation, kind of talked about this when I was just talking about the risks, but so single dual flight computer failure, we have, again, the redundant computers for that reason. Main battery failure, the battery is very much overspecified for the runtime, and loss of main battery does not affect the status of the commercial flight computers. Wiring harness failure, this year we're doing no wire-to-wire splices in the wiring harness. So we're basically just crimping connector pins directly to the ends of the wires. So there's no soldering of wires to other wires. We're also using our connectors. They're all automotive rated, high heat, high vibration. So they're rated for the operating environment that we'll be in. Base structure failure, again, it's really unlikely. The bay is completely aluminum with stainless steel fasteners. It's really rigid and designed to contain the boards in a high vibration environment. Loss of GPS reception, again, I mentioned we have a high gain GPS antenna and redundant GPS sources. Telemetry connection failure, again, redundant telemetry sources on different frequencies. And finally, the CAN bus failure, again, as I mentioned, we have the ability to arm and disarm the commercial flight computers over the backplane without the CAN bus. So our schedule outlook, February through March, we're going to assemble the rest of the boards. So those just came in today, actually, and hopefully this weekend we'll have all of the hardware assembled. We're going to then complete the wiring harness, mount the antennas in the transition section, and complete our critical software functions required for arming and disarming. And then April through May, after the test launch, we're going to complete some more non-critical software functions. We're going to complete our onboard camera system and continue to test our hardware and software. Is there any questions for Avionics?
I have a question.
Yeah.
So I'm a little concerned about your choice of latching relays. I like that they're 50G shock and vibe rated, but the team previously used some solid state relays. I think they were MOSFETs for this task, and so switching to a mechanical device kind of feels like a step backwards. So I was wondering if you could talk about the choice there.
Yeah. So mainly the choice was for loss of power on the I guess the switching side of the relay. because I believe with our previous MOSFET solution, there had to be a signal from the microcontroller to have that MOSFET switched on. So if, say, like the main avionics bay battery failed or something, and the microcontrollers could no longer send that on signal to the MOSFET, then the flight computer would turn off.
Yeah, I'm sorry, that's actually incorrect. The way the MOSFETs worked was that they were active off. So you needed a signal in order to turn them off. So basically, if the arming switch had been like just ripped from the board or whatnot,
right? Okay.
They would remain on.
Interesting. I know at least last year, I don't know about previous year's designs, but last year they were definitely active on. So, but I can look into that. It's not too late to redesign. That's kind of an issue too. I was thinking with then it's kind of difficult to safe the rocket if, again, there's a power failure on the switching side, because then there's no way to, disarm the flight computers.
Yeah, no, that's exactly correct. So we kind of wagered that, if a failure was going to happen, it would happen in flight and not on the pad.
Yeah.
I think that the latching relays are going to work. So I wouldn't worry about it like too much. My main concern is just verifying that shock and vibe and making sure that it's not directional, right? Like, so there's a mechanical thing in there, and if you have that relay aligned incorrectly, it could no longer have the correct rating.
Right. The data sheet. Sorry, the data sheet has a nice graph of X, Y, and Z, and it's actually rated in all directions. But I'm also in contact with there was someone in the mechanical engineering department who now is at Penn State who has a vibe table lab. So I'm in contact with him trying to figure out where that vibe table went, and hopefully we'll be able to test the relays on there.
Yeah, no, that sounds perfect. It sounds like it'll work. The other thing is I would just make sure that it's oriented in a way that the loads, or it's secured beyond just soldering. So sometimes if you have rapid loads and those relays are a higher mass component, they can just break free from the thrust of the rocket, putting loads onto the board. So you just want to be careful of that.
Yeah, we're definitely planning on doing epoxy staking on any sort of component that is higher mass. So yeah, we've thought about that, and that's a great point.
Okay, thank you. I appreciate it.
Yeah, thanks. Any other questions?
Yeah, I had a question. The concern about shock and acceleration is probably real in anything, not just high mass, but high profile. Right. So, and then the second question I had is, are you responsible for deploying the parachute, and what makes that decision?
What are you asking? Am I responsible? Like
how is the decision to deploy the parachute made?
So the parachute deployment is all on the commercial flight computers. So there's the software developed on those. We just set an altitude. I assume it uses a combination of barometric pressure and probably acceleration or GPS data.
Is there a barometer on board?
Yeah. The commercial flight computers both have a barometer, and that's, I think, their main source of determining altitude for parachute deployment in apogee.
Okay.
Yeah.
GPS is not a good way to do that.
Yeah, and I don't believe the commercial flight computers don't base their deployment off GPS. It's all barometric pressure.
And how long is your rocket on the pad before it launches?
I think it can vary from, like, I don't know, anywhere from 1 to 4 hours possibly. It really depends on kind of the range and
it takes a while sometimes for those. It doesn't look like your GPS solution has a pretty, a big antenna, and it might take a while to pick up a GPS signal. And not only that, but you're never guaranteed, you're never guaranteed satellites, right? GPS is, it's based upon what visibility the satellites there are. And if there's not enough in the sky, I'm not sure guys have gotten into the GPS at all, but there's a, you know, a position dilution of precision that you have to deal with, and those types of things. So
Right.
GPS is just, be careful.
Yep. Yeah. Yeah. So again, we're not relying on any sort of like recovery deployment on GPS.
Yeah,
so-
that's good. And barometer is good.
Yep.
So Joey asked a question in the chat relating back to the G-forces and whatnot. Does that include rotational motion?
There was no spec in the data sheet for rotational motion, but I guess you kind of extrapolate like centrifugal force, you know, the acceleration from that based off of rotational motion. I don't know at what rate our rocket has rotated in the past, but I don't think it'd be where the relay is not far from the center point of the rocket at all. So there's not like a long arm where that rotation would impart like a large acceleration on the relay. Any other questions?
Yeah, so I'll try to talk about it. So question for Harrison, related to the environmental testing and the baking the avionics in the paint cure oven to simulate temperatures experienced at SAC. What is the acceptable criteria for this test? I.e., are you using any parameters besides it works, it doesn't work?
Pretty much that. We're going to be monitoring the temperatures. We have multiple temperature sensors kind of built in, like the lithium cells have a temperature sensor in the battery pack. A lot of the ICs on the board have temperature sensors. We've ordered all automotive rated components. So those go up to like, I think 110 or 120 C. And that includes all our microcontrollers and regulators and passive components as well. So we'll probably test kind of about as hot. I don't know exactly how hot our bake oven goes, but we'll go pretty warm, warmer than what we would expect on the rocket. And
how much power are you dissipating? Are there certain components you're worried about?
No, we're not worried about heat generation of the components. We're not dissipating much power at all. It's more of just the when our rocket is like carbon fiber black sitting in the sun in the desert, it's going to get pretty hot inside. So we just want to make sure that the components can withstand those kind of temperatures while we're waiting on the pad.
I would try to find any component. Is any component dissipating a quarter watt or more?
So the telemetry transmitter will dissipate about a watt, but that's also we have a good thermal design there. So we have our wedge locks and really large 4-layer copper pour on that board that will bring the heat out of the transmitter into the actual base structure itself.
If you're dissipating a watt, you better be careful. Anything over a quarter watt typically raises my eyebrow, start to get a little. If you're dissipating a watt on that, I'm not sure what I understand what your copper pores are, but I'm not sure how well they're connected to the wedge locks out on the edge, and the wedge locks they're okay, but you're right to test it, and you should probably assume that is this test gonna happen in the summer, or is it Arizona?
The competition flight is, yeah.
And what time of year is it?
New Mexico.
June.
June?
Yeah.
If you burn one of these things.
What did you say?
Have you used this component before?
No.
Yep, I would do a derating analysis on that component right away. I'd want to see what that thing was doing. Your thermal guys should be able to help you out. Just be wary of that.
Okay, definitely. Yeah, we'll test that for sure.
Alrighty, thank you for the good questions. If you do have any more questions for avionics, I'm gonna have to ask you to hold those till the end because we do want to keep going. But you do have time at the end to ask those questions. But Joe, go
Cool,
ahead.
thanks. Up next is recovery.
Hello, everyone. My name is Mark Wolf, and I am the recovery lead for this year's competition team. So the purpose of our project is to create a functional, reliable, and reusable system to create a controlled descent of the rocket from 30,000 feet all the way to the ground. So we have a slow impact speed, and we can fully recover the rocket so it can be reflown again with minimal damage. We also want to improve from designs from previous years and streamline our integration process. And we also want to create hands-on experiences for students to supplement their learning outside of the classroom. This is our system overview. Our recovery system starts at apogee when our ejection charges will fire and blow the nose cone off. At this point, we will release the drogue chute and slow our descent to 80 feet per second. And then from there, we'll come down to 1,000 feet where our cable cutters will fire, which will release our main parachute. The parachute pilot chute on the deployment bag will pull the bag off of the main chute. And at that point, once we are inflated and fully under main chute, we will be at 15.5 feet per second, which will be our impact speed. And if you notice on this diagram, the drogue chute, the pilot chute, and the main chute are all different colors. And that's so during flight, when we're coming down, we can determine from the ground which systems are active. We can see if the drogue chute has deployed, if the main's deployed fully, what point of the process we're in. So that's just to help us during our flight, so we can make sure everything's going as planned. This is our line configuration when we are descending under our drogue chute. As you can see on the diagram, our drogue chute is going to be attached to our main shock cord using a swivel joint, which will be rated at 3,000 pounds. Our shock cord is made out of tubular Kevlar, which is rated at 1,900 pounds. And then if you come down from the drogue chute, we have 3 feet of shock cord where we'll have the shock cord tied in to a jut off that goes to the nose cone, which will be attached to the shock cord with a quick link at an eye bolt in the nose cone. That's going to be a 3/16 inch quick link rated at 620 pounds. And then from there, we come down 20 feet of shock cord. And this large length of shock cord is to reduce tangling. So when the deployment bag comes off and we're under main, the nose cone and the drogue chute are going to pivot under the rocket body. And that 20 feet of length is to make sure we're not hitting the rocket body with the nose cone or the drogue chute and causing any unnecessary damage. And then, so at the point, the 20 feet of length is going to be tied into a knot with other shock cord, which is going to go out to the drogue chute or the deployment bag, which will be held on to the shock cord by a swivel joint, again, the same 3,000 pound rated swivel joint. And this swivel joint is actually going to be inside of the deployment bag. And this is to make sure that the bag does not rotate at all, but prior to deployment of the cable cutters, because we actually have a wire that's attached all the way from Avionics actually through the recovery bulkhead up that 5 feet of shock cord and the 3 feet of shock cord going onto the deployment bag, which is going to be connected to a zip tie where the cable cutters are connected independently from wires. So we don't want that bag to rotate at all before we release the main parachute. And then after we release the main parachute, we do want that to rotate so that the main parachute can rotate independently of the shock cord and not get tangled up at all. And then finally, if you look at the rocket itself, the rocket body, we have the main shock cord is going to be tied into an eye bolt on the recovery bulkhead. This is going to be done using a quick link, which is going to be a 1/4 inch and rated at 1,000 pounds. This is our main parachute design. We are working closely with Buddy Michelson at Rocketman Parachutes to create this design. He's going to be sending us all the materials that we need to make this chute, and we are going to sew that chute together as a team. So this design has a drag coefficient of 0.97. The material it's made out of is 1.1 ounce ripstop nylon. It has a 16-foot diameter. Our target descent rate is 15.5 feet per second. And if you notice on this picture here, there is no spill hole on this parachute. And that is because the design of this chute is stable and inherently stable on its own due to its shape. So it doesn't require the use of a spill hole at all. As for fabrication of this chute, we're going to be using French fell seams or a French fell seam to hold all the gores together. And this seam is going to be stronger than the actual nylon itself. We're going to be using fabric tape to hold those seams together as we move the gores to the sewing machine. And as we're putting them through the sewing machine, this is to make sure we have a nice tight seam connecting all of our gores and a strong parachute. And then finally, as we're going through the sewing machine, we're going to be using a double needle, which is going to help increase efficiency and speed up the build process so that we are ready in time for the launch. For our deployment bag, we are also using a Rocketman Parachutes deployment bag. We're going to be using their bag that has the pilot chute sewn into the deployment bag itself. It is a square chute. We are going to be getting one that is 16 inches across. And this is to make sure that our parachute is going to be compatible with our deployment bag. The purpose of the deployment bag is to hold the main parachute inside before we want it to release, so before we're under main. And it also is made of Kevlar, so it's going to provide an extra layer of protection from the ejection charge blast of our main parachute, so we don't make any damages and have a nominal recovery. As for our ejection charges, we use 2 separate ejection charges independently wired from the separate flight computers that we employ. We are going to be using this year the ejection canisters that we get from Rocketman Parachutes. They're going to be affixed to the recovery bulkhead using the screw provided, as well as epoxy to hold it in and make sure it doesn't come loose off of the recovery bulkhead during flight. For the ejection charges themselves, they are going to be made using a latex glove with the nichrome E-match inserted with the black powder in the glove and held together using a zip tie, as you can see in the picture. And then once we create those ejection charges, when we get to the integration stage, we're going to put those ejection charges inside the ejection canisters. And then we're going to use a layer of tape over the opening of the ejection canisters. As you see in the picture, there's white tape on the recovery bulkhead. And that is to hold the pressure inside of the canisters so that when we do go to blow those charges, that they can fully combust and we can have a nominal ejection of our nose cone. And so our primary ejection charge is our ejection charges are going to be made using 4F black powder. Our primary charge is going to have 4.5 grams of black powder, and our backup is going to have slightly more at 5.3 grams of black powder. And our primary ejection charge is going to go off right at apogee. As Joe mentioned with the barometer, Avionics is going to give us that signal to blow the ejection charges. And then we're going to have a 3-second time delay on our backup charge. As for testing and validation of our system, we will be doing ejection testing prior to any launches to make sure that we have enough black powder to blow off the nose cone, and also that all of our systems for the ejection are working properly. So this is going to be a ground test about a week before the test flight. And a successful ejection charge test will end with breaking our shear pins and ejecting the nose cone. And then we also are going to use the test flight as a test of the full recovery system, making sure that we can recover the rocket fully. And a successful launch would end with the rocket landing back on the ground with minimal damage, being able to be flown again, just with a new motor. The risks to our project success, there are three main categories of risk. The first one being with our ejection charges. We could have a loss of power to one of or both of our ejection charges. Now, if we were to just lose power to one of our charges, that would be a minimal impact to our project because that is our loss of redundancy. So we still could have a nominal recovery, but we would lose that redundancy there. But this is a low likelihood of happening. As for losing power to both charges, this would definitely be a catastrophic loss of vehicle. Our recovery system would remain inside of the rocket, so we would come down very, very fast and definitely lose the rocket. So we want to make sure that doesn't happen, but this is not likely to happen as it is. Now we could lose power or continuity of the wires. This is a low likelihood of happening, but would again lead to a catastrophic loss of vehicle for the same reason as power loss. We could have run into the situation where we don't have enough black powder. It's not forceful enough to blow the nose cone off of the body. This is not likely to happen. We are doing ejection charges, testing, so this doesn't happen, but this would lead to a catastrophic loss of vehicle. And then also there could be failures with our E-matches in the ejection charges. This is low likely to happen, but would again lead to a catastrophic loss of vehicle. The next category of failure has to do with the main deployment. We could lose power or just a failure of one or both of the cable cutters. If we were to lose power to just one of the cable cutters, this is a minor impact, the same reason as the ejection charges. It's our loss of redundancy, but we still could have a successful recovery, and this is low likelihood of happening. If we lose, or if we have a failure of both of our cable cutters, this would be a catastrophic loss of vehicle. We would come down under that 80 feet per second drogue descent, which is definitely not something we want to happen, but this is not likely to happen. As for tears, this is not likely to happen. Depends on the severity of the tears, but would lead to a significant critical impact to our project success. And then tangles, again, it depends on the severity of the tangle, where the tangling is happening. If it's closer to an attachment point or further up closer to the parachute, it depends on depends on the severity. But it's a low likelihood of happening, but would lead to a significant critical impact. And finally, we have any failures related to our drogue deployment. This could be caused by the shear pins not breaking off, not releasing the drogue chute. And this would be a catastrophic loss of vehicle because we would come in under no parachute, no slow descent, but this is not likely to happen. To mitigate these risks, we are going to test continuity of all of our wires prior to integration to make sure that we're not going to have any problems with any power loss or any connectivity issues. As for nose cone not separating, this is why we employ a redundant ejection charge system. We could run into a situation where one ejection charge doesn't fire. That's the primary, and the backup has more ejection or black powder in it, so that would be able to pop the nose cone off. We could also run into the situation where our primary doesn't, for some reason, break all of the shear pins or doesn't have enough force to fully pop off the nose cone, and that backup charge should come in and do the trick and finish blowing that nose cone off and starting the ejection or recovery process. And this is also why, as I mentioned before, we do ground testing of our ejection chargers to make sure we have enough force to shear the shear pins and start the recovery process. As for any tangling, this year we are focused on reducing our shroud line count on our parachute. Previous years we used a design that employed 18 shroud lines. This year we're trying to get that down to 4 shroud lines. As I showed you in the design before, it has 4 shroud lines on that parachute, and that's to reduce tangling. And then we're also going to make sure we're following our line diagram when we're integrating our system into the rocket prior to launch. We're going to make sure that we have all of our lines in the right place so that nothing can get tangled or have any issues during the flight up, during the initial stages of ejection in the recovery process, and throughout the whole recovery process. And as for tears, there are no sharp edges anywhere in the rocket or anywhere in the recovery system that could cause any tears to happen. So that is not likely. Finally, we have our schedule for the rest of the year. We are going to finish fabricating our drogue parachute. That's going to be done by February 16th. Then after that, we're going to move on to the fabrication of our main parachute. We're going to complete that by March 9th. Then we're going to plan for integration, which will be completed by March 16th. We'll move to ejection testing, wrap that up on March 20th, and be ready for our test launch on March 26th. And then after our test launch, we'll use any observations from that, make any improvements and fixes we need to our system from that test launch, and then complete any documentation or paperwork that we need to complete for the competition. And then we'll leave for competition on June 19th. Are there any questions?
Sorry, I dropped out. My computer kind of died during that, but
Sorry.
no, I don't have any questions.
I know tangling of the parachute's been an issue for the past. What specific corrective actions did you take in order to address that?
So our main thought was that we had, as I mentioned before, 18 shroud lines. So that feels like kind of a lot. So I think the amount of shroud lines was really our biggest concern. So we were definitely looking into reducing that, getting that down to 4 for this year's main design. And then we're also going to make sure we take extra care during our packing process. So if during packing that could have been an issue, we want to make sure that we're packing in a nice way so that it can unfurl without any issue. And then also we're adding the swivel joint. We're going to put that inside of the deployment bag, whereas previously there wasn't a swivel joint attached to the main chute. So that should allow the main parachute to rotate and swivel all at once, independent of the rest of the lines, the rest of the rocket body, the drogue, nose cone. So that should also help reduce tangling. Does anyone else have any other questions? All right, if there are no other questions, then we're going to move on to payloads.
All right, hi everybody. My name is Sarah Malaska. I'm a sophomore majoring in mechanical engineering, and I am this year's payload lead. So for the project purpose for payload, we design and manufacture a payload bay with a 3U Cubesat structure. Using this 3U structure is actually really important because it awards us some bonus points at competition, which will help us to place well. Second, we create a scientific experiment to fit within the payload bay that will be tested during rocket flight. This is really the principal purpose of payload, and it's the most fun part too. We get to be creative and make an experiment to go inside of our bay. Third, we outreach with outside organizations to collaborate on payload experiments. This is also pretty unique to payload. We get to work with students in the community and even other organizations in the past. And finally, like other sub-teams, we educate team members on payload systems and give hands-on experience working with others towards a common goal. As for our overview, the Spaceport America Cup defines payload as being replaceable with a ballast of the same mass with no change to the launch vehicle's trajectory and reaching the target apogee or its successful recovery. This means essentially the payload really has no effects on the rocket launch or flight whatsoever. But our team does have an effect on how we do at competition. We do earn points for our team, and that's important to how we place. The payload also has an 8.8 pound minimum weight requirement and must fill 3 U CubeSat of allotted space. And the payload experiment investigates scenarios and collects data utilizing the unique environment of a rocket launch. It's not too often that you get to actually create a scientific experiment in the conditions of a rocket launch. So that's something really interesting about our subteam. This year, our first experiment will be biological, and we are investigating how rocket launch affects yeast. And the second will be designed by students at Metro High School as part of our outreach. So first off, this is our CubeSat structure. It's a little different from past years in that we're using steel this year rather than aluminum. This will help us actually get up to our required weight requirement that I mentioned before. Most of this bay has been machined by our subteam, apart from the water jet cutting and the welding. We actually welded the joints between the rails and the faceplates here on each of those. So it should be a strong connection there. The bay itself is approximately 3.2 pounds, which is 43% of our minimum weight requirement. And when you combine this with our allowable dummy weight, we actually achieve 68% of the required weight. This will be really helpful in helping us to get to that 8.8 pounds. It's a pretty large weight requirement, especially for such a small system. And like I said before, this will hold 2 experiments. 2U will be used by us for the biological experiment, as well as the dummy weights. And 1U will be left for the students at Metro High School. So the first part of the yeast experiment, we will be testing 1 or 2 strands of yeast. These were both recommended to me by an OSU microbiology professor. The first of which is Candida albicans, which is a normal resident of the human gastrointestinal tract. And the second of which is Saccharomyces cerevisiae, which is otherwise known as brewer's yeast. These both can survive in pretty similar environments. They both have a maximum growth temperature of about 110 degrees Fahrenheit, although Candida albicans can survive higher temperatures before death than brewer's yeast can. And these yeast samples will be contained in an airtight insulated box, as shown here where the laser pointer is. This box will be created by coating a 3D print with epoxy in order to seal the holes that would otherwise be in the plastic, since we do want it to be airtight. And we will then seal between these 2 parts here using a rubber seal, and then latch it with the latch that is shown. And that will, again, help us to create an airtight seal there. And we will then utilize aerogel 6mm insulation, which is a really powerful type of insulation. It's very low density and also is very thin, which is very helpful for our small space. And since the box will be airtight, the yeast will be undergoing fermentation and producing CO2, which is something that we'll be measuring along with temperature and pressure data. And then finally, we'll use methylene blue to dye the cells post-flight to test their viability. And that viability will then be compared to control samples that we have on the ground. And we will see if there's a difference between how many cells are alive versus dead. As for the electrical component, like I mentioned before, we'll be gathering data on temperature, CO2 output, and pressure. And to do this, we'll be using a DH22 temperature and humidity sensor. This operates from -40 to 176 degrees Fahrenheit. So since the temperatures at launch do get high, this should have no problem measuring those high temperatures. We will also then use a high precision barometric pressure sensor, and this will be used to ensure that we do have an airtight seal in our box. If the seal is airtight, we should keep the same pressure throughout launch inside of that box. And then finally, we'll be using an analog CO2 gas sensor. This is highly sensitive to CO2 and less sensitive to alcohol and CO. And this is very good for us since during fermentation, yeast actually outputs both CO2 and alcohol, but we are only trying to measure the CO2 output. For these sensors, we'll be using a TNC 3.6 as part of our final circuit. This is the same microcontroller that we used last year on the Vibes experiment. But we will be creating a proof of concept using Arduino, but the TNC has a greater accuracy and processing power than an Arduino Uno does. And data will then be logged using SD card, also very similar to the experiment setup from last year. Like I said before, we're also outreaching with Metro High School. So we'll be working with students in the mechatronic class at Metro, and they will be designing our second experiment. So essentially we'll be going to their class once a week for 4 weeks, actually starting tomorrow morning, which is pretty exciting. And it'll give give the students a chance to use the skills that they've learned relating to both CAD and Arduino to design our second experiment. And then after they design it, we will actually be building it. As for testing and validation, we will both be pressure testing and temperature testing the fixture that will hold the yeast. Since we are making an airtight box, we have to make sure that the 3D print is able to withstand the pressure difference between the inside of it, which will be ground pressure, and the pressure at 30,000 feet. To do this testing, we will use the team's vacuum pump to reduce the pressure inside of a testing vessel, which will be something pretty simple, like a box or a frame that then has a vacuum bag over it. And our 3D printed fixture will be inside of this frame. And then we will then use a pressure sensor to record the pressure inside of the print, ensuring that the seal is airtight. And we will use the pressure gauge on the vacuum pump to track the pressure inside of the box outside of the print. As for temperature testing, we will be doing something pretty similar to avionics. We'll be using the oven at the CDME to heat up our insulated print to see how it withstands high temperatures. This is just to ensure that the inside of the printed fixture does not reach the same temperatures as inside of the rocket. Temperatures inside of the rocket can reach up to 140 degrees Fahrenheit, since it does sit on a launch pad in the hot desert. And we use a temperature sensor inside of this fixture to record any temperature changes and see how hot it gets. So we do have some risks to our project success. First is sample death due to high temperatures at launch site. Note that sample death doesn't result in a loss of vehicle, but it does result in a failed experiment. And that's the reason it's not in the catastrophic column. The rocket would still launch, we just would not have a good experiment. Our second risk is high pressure inside of our airtight container. Like I was saying before, there's a pretty stark pressure difference between the inside of our container and the outside at 30,000 feet. And we need to make sure that the print is able to withstand that. Third is electrical system failure. This is a low likelihood, but it actually wouldn't have a super critical impact. Since we're also testing the viability of the yeast, if we don't get data back specifically on the CO2 output, we would still have data on how the yeast survives the flight. Obviously, that's not something we want to happen, but our experiment wouldn't be considered failed if that does. Fourth is structural failure. This is actually the only thing that could result in a loss of vehicle from the payload subteam. Since the payload bay is actually above the avionics bay, if some sort of structural failure were to happen, it would likely also have some sort of impact on the avionics bay, which would have some sort of impact on the rocket. But since we're using a steel bay that is also welded, that's very, very not likely to occur. And then our final risk to project success is scheduling issues with Metro High School. I included this since we actually were pushed back 1 week from our original start date with them due to the snowstorm last week. So it kind of goes to show how we don't have control over their schedule. I don't expect this to have a super critical impact on our experiment though. Because even if we are pushed back, we should still be able to complete something. And if something does happen where we can't work with them, we can always create a second experiment on our own or expand our biological experiment. As for risk mitigation, like I mentioned before, we will be conducting temperature and pressure testing. I explained those pretty well before on a few slides back, but those will both help us see how our 3D print that will hold our samples can hold up to those conditions. We'll also be including sample redundancy in case of sample death. Since yeast is a living thing, we can't control whether it lives or not. We will try to keep it alive the best we can, but we'll include other samples in both the rocket and control populations just in case something does happen to maybe one population. And finally, we will test our structure just to make sure all the components are secure and won't come out of place during flight. And as for our schedule, so now in February, we are working on welding the payload bay, which was actually completed today. So I guess that's kind of checked off. We will also be doing outreach at Metro High School, which starts tomorrow morning, like I said. So also should be finishing up that pretty soon. We will print our fixture to hold our yeast experiment and then coat that epoxy and get that ready in every way that we can. And we'll be working on our proof of concept electronic sensors. So that will be done with the Arduino. In March, we will conduct our pressure and temperature testing on our fixture, begin the final electrical component that we will actually use in our launch, And we will build the design created by the Metro High School students. And then at the end, we have our test launch, which is pretty exciting and gives us a chance to see how we're doing. In April, we'll finish all construction. We'll do some final testing and any final design changes to get ready for our competition in June. Are there any questions for Payload?
Sarah, John Dilly, are you going to have the yeast fermenting during the flight?
Yes, after talking with the microbiology professor that I mentioned before, he thought that it'll be best to keep them in a airtight container so there's no big pressure difference. We don't have too many variables changing. And when it is in an airtight container, it will undergo fermentation since it can't undergo respiration.
Okay, well, I guess what I was leading to is that if it's fermenting and it's generating CO2, the pressure is going to go up. Think of a champagne bottle. So as it generates CO2, it's going to increase the pressure inside, even above atmospheric if it's a closed container. It's not a fast process, but it does increase the pressure.
Yes, you are right. I guess with that, since rocket flight isn't a super long process, I'm assuming. I know it can be on the pad for a few hours. We were kind of considering that to be something that shouldn't affect the pressure too much. If it does affect the pressure, that's something that will be measured with our sensor and we should be able to see that. But that does bring up a good point.
Yeah, a couple hours isn't a long time for.
Yeah.
It is a long time for fermentation. It's kind of a slow process, but it does CO2, which will increase the pressure.
We'll look more into that. That's a good point. Thank you for bringing that up.
I've got experience making beer and wine, so I might be able to help.
Yeah, probably more experience than I have with you. So I appreciate you bringing that up. Thank you. Sure.
Joey here, old actual payload lead for the electronics. A couple questions. How first are you fixing all the different sensors and getting all that first of all wired? I guess maybe first of all, how are you getting it wired inside the airtight container, and then also making sure how is that affixed then and connected to the Teensy board, and then how are you making sure the SD card is still staying connected throughout the whole flight?
To be completely honest, I guess with the SD card first, we're planning on using a pretty similar process to last year. That is something that we still have to do a lot more research in. I'm not going to lie to you there. And as for the sensors, we would like them to be inside of the box. We were thinking of creating, I guess, some sort of seal, maybe using rubber or epoxy where we could, I guess, kind of lead the sensors through into the box. That is something that we need to look more into. And we definitely will be moving forward.
Not too worried. Oh, and then the last kind of question there, how are you going to actually get that all attached? Are you using like a proto board, or are you going to have a PCB? How are you going to get that all then reattached to the actual TC board?
We'll likely start with a proto board and just work on soldering there. I think we do want stronger connections than a proto board, I guess, with soldering would give us. So we'll likely test that first at the test launch, and then go from there depending on time too.
Okay. And then I guess one final question, just a flight critical one. This shouldn't really require probably calculations, but just make sure you don't smush the avionics.
Yeah.
Yeah, just do a quick hand calculation on the G's when you're actually flying at the full Mach, whatever the heck Mach speed we fly at. How many G's we'll be pulling. Just make sure you don't smush them. That'd be bad.
That would be bad. The goal is to not smush them. You're right. We will also do that. Thank you for bringing up all those points.
Yep.
I had a couple questions. You said it was 140 degrees Fahrenheit inside the rocket. Where did you get that number?
That data actually comes from temperature data that we got at our exhibition flight last year. The temperatures are definitely not the same. But at the exhibition flight, we had a black rocket in the sun with I think outside temperature of 55 degrees. And I believe that the temperature inside of the rocket was around 80. So about 25 degrees higher. So we kind of use that data to come up with the 140. And then
good. Now, what about you said you were going to 3D print the vessel for the Yeast?
Yeah, yep, that's
Out
the
of,
word.
out of what?
ABS.
Plastic?
Yeah, yep. According to just research, ABS should be able to withstand those temperatures.
Oh, it's the pressure I'd be concerned about.
Yeah, actually, let me go back a few slides. I didn't really mention this while we were on it, but using an ASME, I guess, pressure calculator, we found a pressure rating on, I guess, a cylinder with a diameter or a wall thickness of 0.1 inches to have a pressure rating of about 61 PSI. So it should be it should be able to withstand the pressure difference, but that's also why we're conducting pressure testing.
Okay, good.
Hey, this is here one follow-up question on that. So you will see at those temperatures, you're still going to see some sort of thermal deflection. So and especially with those seals, any sort of movement might be a concern. So is there any cost or schedule implications of trying to run a control test in your oven with the yeast ahead of time in order to predict, say, some of that movement and make sure you have a vacuum under temperature?
Do you mean like a deflection in the 3D print, like that fixture kind of deforming?
Yes. So just the natural expansion of the print in the heat, and then making sure that you still have a good contact seal when that occurs. And also too, with the consideration that the yeast will build up pressure on the inside of the vessel.
Yeah, we weren't originally planning to temperature test with the yeast inside of the fixture. That is something to consider with the pressure buildup, actually. But I guess we were hoping that doing temperature testing would show us any deformations that would occur. And then we could also pressure test, I guess, after we do temperature testing, just to make sure that the seal does remain airtight. Maybe we could do those close to one another. That is a good consideration to look into.
Do you know how quick it's Joey again. Do you know how quickly the yeast will ferment? I just wanted to ask, because I'm just thinking again, going back to that pressure, it shouldn't be much. Well, I guess I shouldn't rephrase that. I don't know how much that will be, but I just wanted to ask if there is any knowledge on that.
I don't have an exact number for you, honestly. I guess when we were planning the experiment, we were assuming it wouldn't be on the pad for about 4 hours, but I guess that's not really knowledge that we have. So we will look more into that, since that was a really good point to bring up about the pressure buildup. Yeah, that's definitely something we need to research more.
Well, hey, let me jump in here. Once you start the fermentation, you need to have some sugar in there for the yeast to convert the CO2 and alcohol. It takes on the order of a day to get it started. It's not super fast.
Yeah, we should have, we'll have the samples like before going down to competition. So they should be, I guess, undergoing fermentation for more than a day at that point. And we'll be using probably agar. There's certain, I guess, like formulas of, I guess, sugars that I found just through research that we'll be using that yeast, I guess, does well off of. But we will be giving them sugars for them to convert. Are there any other questions for Payload?
Real quick, have you guys printed with ABS before? I just know that it's a very finicky printing process, and I've seen a lot of warping and stuff, my own prints, printing with ABS. So I was just, if you haven't already, I would just check it out.
Personally, I don't recall if I have printed with ABS, to be completely honest, but
yeah, so we partner with CME, Center for Design and Manufacturing Excellence here on campus, and they have some nice ABS printers that we were able to use.
Awesome.
Yep.
Thanks, Casey.
Of course.
Are there any other questions? If not, I will pass it off to Propulsion.
Thank you. All right.
All right, hello, everybody. I am Noah, and I am the propulsion lead. So the purpose of our project is twofold. It is to first research, design, build, and test the solid rocket motor. Second, it is to give students hands-on experience in the world of rocket propulsion. So for our structural components, we have our motor case. This is a 54-inch long aluminum tube with a 98mm outside diameter. This is going to be used to house all of our other propulsion components. Then we have our forward closure, which is also made out of aluminum. This will be used in conjunction with the O-rings you see down here, and the retaining ring to seal the forward end of the case so that no hot gases escape into the rest of the rocket. For our propulsion components, we have our nozzle, which is machined out of graphite. This will act as the rear closure to our motor case. And then for our fuel, we use ammonium perchlorate composite propellant. It is in the form of solid propellant grains with a tubular grain pattern. And as the grain will burn outward from this inner circle you see here, our grains will effectively act as the combustion chamber for our rocket. Here's a better view of our system assembly. So in the middle here, we have the motor tube and the liner. And down here, you can see we use an 8-grain motor with O-rings that go on our forward closure and nozzle, both of which are secured in place by 2 snap rings. And this top picture is a translucent view of the full assembly. For the scope of our project, last year, when we did our full-scale static fire test of last year's motor, the data we received indicated that the motor was burning much hotter than anticipated. So in an effort to improve combustion stability, we have changed our metal fuel from magnesium to aluminum. And we've also decreased the total amount of metal content within the formula to reduce the combustion temperature. As always, we will be prioritizing motor reliability over altitude goals. We would rather have our rocket get off the ground and miss a few points than not be able to get off the ground and get 0 points. We will also continue developing our static testing related skills and experience. We do this through 2 different kinds of tests. The first being characterization testing, in which we test subscale models of our motor. And then the next one being full-scale static fire tests of the flight motors, which is just to test our full-scale motor and make sure that everything scales up, the performance of the propellant scales up from the subscale characterization tests. Moving on to testing, here's some nice pictures of our static testing. So we use BurnSim to simulate the performance of our motor before we test it. BurnSim has given us these wonderful values. You see we have a total impulse of 17,555 Newton seconds and an average thrust of 3,096 Newtons, or around 700 pounds. So this motor would be classified as an N3096. Its burn time is 5.67 seconds and its max pressure is about 509 PSI. You can see over to the right here, we have our progressive thrust curve, which is due to the type of grain geometry we chose, the tubular geometry, and our pressure curve. Now, the risks to our project success, the worst case scenario would be a motor explosion / CATO. You see down here, that is in not likely, but it would be a complete and catastrophic loss of our vehicle. Our rear closure failure, or if our rear closure fails, which is in the low likelihood category, it would have a significant critical impact, but it wouldn't necessarily destroy the vehicle. An ignition failure is not likely, and wouldn't pose a critical impact. Its impact would be non-critical to the competition. And lastly, we have insufficient or excess thrust for our 30,000 feet goal. This one is low likelihood. We will likely not nail 30,000 feet exactly. But if we are up or down a couple thousand, it's only a minor impact. Then our mitigation plans is just to do as much testing as we can possibly do. So we have scheduled right now 2 subscale characterization static fire tests. These will be 75mm motors. They will be 2 different forms of our propellant formula. One will be slow burning and one will be fast burning. At least 1 full-scale static fire test. We would prefer to have 2 full-scale static fire tests, but working around the schedule with our partners, it's not always easy to nail down a hard date. So the second test is currently tentative. And lastly is our test flight. This isn't necessarily used to validate the performance of our motor, more than it is to validate the performance of our motor assembly in a structural sense. So making sure that our forward closure is working together with our O-rings and sealing the motor tube nicely, making sure that no hot gases are escaping into the rest of the body of the rocket. And the motor that we'll be running for this test flight will only be a 4-grain motor instead of our full-scale 8-grain. And that brings us to our plan for the year. So currently the propulsion team is designing, building, and testing a small-scale rocket nozzle test stand where the rocket nozzles will be removable and replaceable and 3D printed. In early March, we have those subscale characterization tests. Again, 2 75mm motors. In the middle of March is our first full-scale flight motor static fire test. This is mainly to establish confidence in the scaling of our propellant formula performance to a larger length to diameter ratio. Then we will have our test flight in late March, and hopefully after that, we plan on after that having a second full-scale flight motor static fire test. This will just be used to test any warranted changes to the propellant formula that we noticed may be necessary after the first full-scale static test. And lastly, we will be traveling to Dayton somewhere between late March and mid-April to learn more about motor casting procedures, because we want to make sure the propulsion lead and everybody on the propulsion team are well-versed and fully informed and participating in the motor construction process. Any questions?
Yeah, I had one. You said that the motors were burning too hot. How do you know that?
This is from data from our a full-scale static fire test that we did last, I want to say November, or it may have been second semester of last year.
So what was the result of the motor burning too hot?
The result, I'm not really sure what you're asking. It was
like, did it blow up?
No, it did not blow up. It raised concerns because what we had simulated with BurnSim prior to that test predicted a vastly cooler burn for that temperature and a lower rated average thrust, or was it? Yeah, average thrust.
So your thrust was above what you thought it would be in the test flight.
Yes.
Or the test, not test flight.
Yeah, in the static test, yes.
Okay.
Hey, it's Todd here. I'll help out a little bit. It was the pressures were so much higher, and pressure goes up, temperature goes up. Hotter is kind of a generic term that we use. The pressures were just getting to the point where we were worried that we're going to have the same problem that we had, I guess, 3 years ago now. We just wanted to get the pressures back down to a more reasonable level.
Yeah, and to expand on what Todd was saying there, I don't have it on here, but I can tell you, last year's motor ended up being a 97% end motor. I can't do the math in my head right now, but it was close to 3,000 more Newton seconds of total impulse. The average thrust is around the same now in this simulation. The burn time is 5.67 seconds, which is about a second quicker than our motor last year. And the maximum pressure is, I believe, about 80 PSI less than our motor last year. So we were able, at least in the simulation so far, to reduce that pressure.
And is that maximum pressure within what percent of the structural capability of the motor tube?
I'm not sure what would be the point of failure in our motor assembly. I would assume that it would be forward closure failure before motor tube failure. I'd say probably around 800 PSI.
And I just didn't know if we're talking, if you had an idea, if you were even close. Probably not even close, but
no, this should be well under our motor assembly's capabilities.
Okay.
Any other questions about propulsion? All right, hand it off to Casey.
Yep. Alrighty, so I'm going to go ahead and open the floor up to any questions that anyone might have regarding any sub-team that you want us to go back to. Same as before, anyone feel free to ask, and I'll bring up the correct lead to answer your question.
Well, I just want to say awesome. Good luck to you guys real quick. I did have two kind of questions. One was for structures. I don't know if I didn't catch it or not. What is transferring the load from the motor to the rest of the assembly? I know there's the coupler in there and the transition. I didn't catch either how they made it or where that force is being transmitted up.
Eddie, you want to come over here?
Yeah, exactly what you said. The coupler is what's transferring the load between the two, and then the transition is just there for aerodynamic purposes.
Okay, very good. And then the other one was, I know you guys said you did some static stability testing. Have you guys looked into any dynamic stability? As far as like mid-flight, I assume that the fins are, they're non-actuated,
Right.
but anything to kind of keep it a bit more stable during flight.
No, we haven't looked into any dynamic stability testing. I know that if we get in wind tunnels, we could probably do something like dynamic stability test. But I guess until we get that capability, I don't know any way to test the dynamic stability.
Understood.
I got a question. Who's
Yeah,
the
John, go ahead.
engineer?
I'm sorry, say again.
Casey, are you the system engineer?
The system engineer? I guess I would be.
Okay, well, so after you do the static firing and you have a flight test, seems like you need to update your parameters to see how high it's going to go. In other words, you got to do an iteration there to update the trajectory based on the latest data you have.
Yeah, exactly. Part of my job then is making sure that data gets disseminated from avionics to aerodynamics to ensure that we can cross-check and cross-reference. So yeah, you're exactly right.
Okay.
Thank you. Other questions?
Is there a prediction of what altitude you're going to go to?
Yeah.
You probably was, and I just forget it because it was so long ago.
You're right. Yeah, I was back in the beginning. Zach, so our open rocket simulation predicts we're going to go 29,282 feet. We're looking to validate and also compare with our aerodynamic simulations that we'll have in the coming weeks But for now, open rocket's pretty standard about whatever one uses. So that's what we're running with right now.
And the goal is to be right at 30,000, right?
Yes, there's a scoring equation, which is kind of complicated. But the closer we are, the more points we get, and we want to win first place. So we want to be as close as possible within reason. We're not going to make sacrifices in our structural integrity or our motor integrity like we may have done in 2019, which caused our downfall that year. So we want to make sure we're as close as possible within reason. And it's a hard to predict number too, with the variables that go into the motor, but also the air in the atmosphere, just predicting that drag accurately. Open rocket is good, but it's not perfect. So that's part of why we're doing so much work this year with aerodynamics. Does that answer your question, Craig?
Yeah, no, absolutely.
Okay.
I was just thinking about the aerodynamics point of view, and what matters here. And I'm not sure if the density and temperature of the air is taken into account during that.
Yeah, in our simulations, we do model air as an ideal gas, and so we change both the temperature and pressure we're operating at, so that effectively, because of the ideal gas equation, changes the density. As for when we build our altitude predictor, whether we'll take the pressure variation into effect, we still have to figure that out. If we go to the coefficient of drag plot that I had, I don't know if you can scroll to it fast enough.
Go back and forth. Sorry.
There is a slight difference between, you can see like this data point versus this one are around the same Mach number, but this top one is closer to the ground and the bottom one is closer to apogee. So there is a difference there, but it's not great. It's not like a super significant impact, I guess.
Okay.
And so we got a question in the chat from Alan, I believe. Do you want me to go back to your slide?
Yeah, so I think the question was, what is our descent velocity, target descent velocity? So under drogue, we're looking at an 80 feet per second descent rate, and then under main, we're looking at 15.5 feet per second.
Other questions? Nick, I saw you unmuted. I'm going to pick on you now. Any questions from anyone?
Yeah, I did have one. I wanted to give you guys a chance to make sure you answered that. I guess it's less of a question, more maybe a comment. I know Structures mentioned building or feeling a little bit more confident about the transition piece. I want to kind of relay that, you know, if you're making a new mold, and that process alone tends to be some of the your plug especially tends to be one of the hardest things you're going to end up doing, because every imperfection you have there will magnify as you go along in that process. So I wanted to just express any interest in saving time there. Make sure you've got a little buffer, because it may end up taking longer. But overall, I thought, I do want to say that Structures and the rest of the presentation was really great. A lot of improvements been put in, a lot of work's been put in since PDR. So congrats.
Absolutely, I agree, and thank you for the kind words. Real quick, also congratulations to you, by the way.
Yeah, thank you.
One quick question: how much does a rocket weigh when you pick it up off the ground after it comes back down?
Mark, I think it's in your slide somewhere, right?
I'm not sure. It's should be 48.6 pounds is the dry weight. I don't think it's
okay.
But yeah, just under 50 pounds.
So it starts off at 70 and you lose about 20 pounds.
Yeah.
Yep, exactly.
Okay, thanks.
Any other questions? Going once, going twice. The third and final time. All right. We'll go ahead and wrap it up here. Once again, thank you everyone for coming out. We appreciate you being here at our CDR. Sorry it took a little longer. We elected not to take a break due to being on Zoom this year in the middle. But if you do have any other further feedback, I'll send out, if you're on the email list, I'll send out another email. Feel free to reply to that or send it directly to me. Either or works. Yeah, we appreciate you all coming, asking questions.